Dr. Moiya McTier.
You're so tall. What are you doing up here?
Is there anything you would
No. That way you can see the skirt. It's important.
Yeah.
Okay. I'm going to be talking about the fact that there is a naming problem when it comes to dark matter. So dark matter and names matter tonight. Of course, I'm going to start, with a brief little history of how we have understood the composition of the universe. And I'm going to go back a few thousand years, where for a long time we just didn't really know what was happening. A lot of people either didn't ask what things were made of, or they were like, well, there's God stuff, and then there's us stuff, and we're going to play with the us stuff. And why think about anything else? But around 400 BCE, before Common Era, this dude Empedocles, with some contemporary thinkers, imagined that there were these four basic substances, the four basic elements: earth, air, water, fire, and all of the things that we see, all of the us stuff, is made up of different combinations of those four things. Very soon after that, just 50 years later, this guy Democritus is supporting the idea of atoms, atomos. These are the most basic building blocks of everything that could exist. They are indivisible. That's what atomos means. And he was promptly ignored for 2,000 years. Because of Empedocles, we were plunged into a dark time of elemental mysticism that we could have gotten out of because of Democritus, but no, everyone was like, an atom, that's ridiculous. Obviously, everything is made of these four elements. Aristotle came along and he added the ether, the stuff that the universe might be made of. But for 2,000 years, we were like, yeah, everything is just these 4 or 5 elements. Until 1803.
Wow.
I'm not joking when I say 2,000 years. This is when the first person, for the first time, John Dalton, proposes something that is akin to our modern atomic theory. He's like, there are these tiny little indivisible pieces of stuff, and we can understand their structure, and we can understand how they combine to make different things. And thanks to him, we then entered a phase of understanding what matter is. We were like, okay, we understand that it's not just God stuff and us stuff, and it's not just these 4 elements. We know about the physics of matter. And then in the 1970s, the universe was like, psych, nah, you don't understand anything. Actually, most of what you've seen is a type of matter that is very rare in the universe. This is when we got, for the first time, empirical evidence that there's dark matter, matter out there that can interact gravitationally, but we can't see it. The empirical evidence that got everyone to agree dark matter was a thing came from Vera Rubin studying the rotation curves of galaxies. So she was studying how fast are stars moving at different parts of the galaxy. And we would expect that stars further out, thanks to the Kepler lesson that Mark gave us, we would expect that stars further out are moving more slowly. But what we see is that they're moving faster than we expect. So there's some mass out there because, again, thanks to Mark, we understand that... Yeah.
I'm just lobbing them up and you're knocking them out of the park.
Thanks for the assist. Thanks to Mark, we understand that the speed at which you travel in an orbit is based on how far away you are from the thing and also the mass of the thing in the center. And then we were rocked. We were like, oh, we don't understand matter at all. And then even more than that, in 1998, we realized that the universe isn't just expanding at a constant speed. It's getting faster. That's something that shouldn't happen according to what we understand about the laws of the universe. So there must be something extra, this other force that is propelling the accelerated expansion of the universe. And we learned that we really know nothing. And so now we understand that this is the composition of the universe. It might be a little hard to see, but about 5% of it is visible matter. Astronomers or other physicists might call it baryonic matter. That's just regular stuff like you and me. We interact with gravity, we interact with light, we interact with all of the fundamental forces because we're boring. And then 27, is that what it says? 27% is dark matter, which is matter just like us, but we can't see it. And then most of the universe, 68% is dark energy, that force that is propelling the universe's expansion. And they're not going to tell you this in school. But there's a very, very tiny fraction of the universe that is held together by the egos of scientists. And they don't want you to know this because it would underpin the entire galaxy.
Yeah.
And then it would fall apart.
I'm
So-
surprised this platform can hold all of our egos right now.
Yes. It's because we're well balanced.
Well, our heads are so inflated that we actually are counteracting the weight.
And so you're saying if you're not on this stage, you don't matter?
Oh.
Ooh. Yeah.
But you might energy if you're not on the stage. It's important to remember that in this context, matter and energy are not the same thing, despite what Einstein might have you believe. Here, dark matter and dark energy, very different things. Dark energy is the force that is making the universe expand faster than it should be, and dark matter is the stuff. It's the stuff in the universe that we just can't see. And it has gravitational force. That's a really important point, because the only way we can study it is by seeing how it influences things around it, how it moves stars, how it moves galaxies. But we don't know what it is. We've spent the last, 50 years trying to figure out what is dark matter made of. And there are some criteria that a good dark matter candidate should meet. So if you want to be a good dark matter particle, you cannot interact with light, with the electromagnetic force, and we've also observed that dark matter doesn't really interact with cosmic rays. Those are these really energetic particles that pass through us, actually. They pass right through us. Most of them pass right through the Earth, but they're zipping around the universe all the time, and they don't seem to be affected when they pass through dark matter. It also has to stay relatively cool. What we know about dark matter now and how it contributed to the evolution of the universe is that it was very present early on. The early universe was much hotter than the current universe, and in order for galaxies to coalesce and come together, they needed a cooler scaffolding to build onto, and we think dark matter was that cool scaffolding. It also has to be really abundant. 27% of the universe is made of this stuff. 90% of the matter in the universe is dark matter. So that's what we're looking for when we're looking for a dark matter candidate. And the particle physicists, they've been busy. They have been coming up with a lot of different ideas.
So I just want to point out, Moiya and I played D&D together, and I can't help but notice that a good DM candidate doesn't interact with light, stays relatively cool. I don't know if I understand the abundant in the early universe thing. But
It's world building.
That's true. They're
just
always
world
having
You
to
have to
come
be
up
there
with
at the
cosmologies.
beginning.
That's right. Yeah. Okay.
Yeah.
So do you feel like you are a good DM candidate, Noah?
I am interacting with quite a lot of light right now, and it's making me sweat.
All right, so no. But that's okay, we'll still play.
Okay.
Yeah, I think Noah is a great DM. So one of the potential dark matter candidates, actually one of the first ideas for what is dark matter that was proposed, is something called a macho, a massive astronomical compact halo object. These could be primordial black holes. In fact, at first it wasn't called dark matter. It was called something in French that I'm not going to try to say. But it was, first it was called dark bodies when we first started noticing that there were discrepancies in how things moved in space. That got translated into French, and then that got translated back into English as dark matter. So these machos could be black holes, they could be big invisible particles that we don't know about yet, but this has kind of been debunked. We are pretty sure that dark matter is not a bunch of Johnny Bravos out in the universe. Then there was another idea. We were like, maybe, let's swing to the other side. Maybe dark matter is a bunch of weakly interacting massive particles, or WIMPs. And there were a few different particle candidates in this, but they don't really interact through the fundamental forces, through like the strong and weak nuclear force, and that's why they're weakly interacting, and they don't really interact with themselves. But we couldn't come up with any good particles that we knew of that would meet these criteria. So then we decided that we have to just make up a new particle if we really want to understand what dark matter is. And up until now, up until the 70s, all of the particles that we knew about fit into this little picture. This is the standard model of particle physics. There are Higgs bosons, there are photons, there are baryons, there are mesons, there's a bunch of different types of particles. But there was a problem with this model, and the physicists called it a CP problem, which is already a little sus to me, because we do know that particle physics had like A CP problem, yeah. We know, like there were not enough CPs in particle physics, but that's not what they meant when they said CP problem.
Oh no.
Their CP problem stood for the charge parity problem. Basically, particles were too symmetrical in the universe. So they decided to create this law where particles have to be symmetrical, and if they're not, then something breaks, and when that happens, a new particle is created. This idea, this solution to the CP problem, was come up with in 1977. They said that this particle that's produced when this rule is broken, and it should be broken often, it would be a very light particle, and it would be so abundant because this rule gets broken all the time. So it's a good particle candidate for dark matter. And we had some ideas for what we could call this particle. Someone said, let's call it the Higglet, which is really cute. Like, that's an adorable name, and it invokes the Higgs boson, which some people call the God particle. It's this really important thing in particle physics. And then this dude named Frank Wilczek, probably. I didn't want to look up how to say his name. He decided.
Why that one?
What?
What you did? That was a random name?
No, that's his
Oh,
name.
that's why you said you didn't want.
We're not gonna
Probably.
pronounce it.
But I don't
Oh,
know.
got it.
There's a C and a Z in there, and I
Got
don't
it.
care.
Okay.
Because this man decided to solve the already suspicious CP problem with a particle that he thought should be named after a Latin American soap. He was like, let's name this particle after a soap brand from 1968 that you can now only find in Latin America because it cleans up the CP problem. And I can't be the only one who sees an issue with this, right? Right? Like, there's something suspicious. It's a little hinky, right? Like, I don't think they did this on purpose, but it's definitely a naming problem. And I am not the only one who has noticed this. There is a very well-respected particle physicist and cosmologist, Dr. Chanda Prescott-Weinstein. 2 years ago, she came out with this book called The Disordered Cosmos, which I highly recommend. It talks about cosmology, it talks about theoretical particle physics, it also talks about the social issues in astronomy. And one of the things that Dr. Prescott-Weinstein has been pushing for a few years is changing what we call dark matter. This is a plot in the book of hers that shows all of the different potential candidates for dark matter, and all of them have a naming issue because we're calling it dark matter when we should be calling it transparent matter. It's not inherently dark. It's invisible. We can't see it. It doesn't have a color. And calling it dark just because we don't understand it, while not explicitly racist, is still a little bit fucked up. Because it's something that we use in a lot of science where if we don't understand what it is, we're like, well, that's dark. That's the dark thing. That's the black thing. And then we continue to have things like CP problems in physics. So, my whole takeaway from this talk is probably read this book and be an evangelist for calling it transparent matter instead of dark matter, because not only is it kinder to the people who study this, but it's also more accurate as a description. It is not dark, it's transparent. Thanks.
Give it up one more time for Dr. Moiya McTier and transparent matter.